This episode will look at proof by induction applied to differentiation and trigonometric identities. I will obviously keep the same structure of n equals 1, assume true for n equals k, and prove true for n equals k plus 1, but I'm also going to apply the same 4 points that I discussed in the last episode that deal with when n is equal to k plus 1. The first example looks at the nth derivative of a function. You need to have studied differential calculus before to access this question. The concept we need to use is that the first derivative is found by differentiating the original function. The second derivative is found by differentiating the first differential. And the third derivative is found by differentiating the second derivative, and the process continues. You get the idea of what's happening here. And maybe you can see a relation to proof by induction where one domino directly affects the next. But let's start the process. I can start by looking at the left-hand side and the right-hand side. For the left-hand side, I need to evaluate the derivative of the function x squared e to the x. Here I have the product of two functions, therefore I need to use the product rule. I can now evaluate the right-hand side by substituting in n equals 1. I get the same as the left-hand side, therefore it is true for n equals 1. My assumption for when n is equal to k is that the derivative of x squared e to the x is equal to x squared plus 2kx plus k times k minus 1, all times by e to the x. As I have done in previous questions, I've put down the goal here, what I'm heading towards when n is equal to k plus 1. Firstly, we're going to substitute n equals k plus 1 into the left-hand side of the statement. And then I need to manipulate to try and work in the left-hand side of the assumption. And I'm going to use what I talked about at the beginning of this example, that to get from one differential to the next, I need to differentiate. So to get to the k plus 1th differential, I need to differentiate the kth derivative. I can now substitute in the right-hand side of my assumption. And the final point is that I need to work on manipulating this in order to get my goal. So obviously now the thing to do would be to differentiate my function. And I can see here a similarity that my goal is just one expression. It's one bracket times e to the x. And at the moment I have two brackets, or I have two things multiplied by e to the x. So I can factorize out e to the x and then simplify the inside of my bracket to get my goal. The key point in this proof is manipulating the k plus 1th differential. And I advise you to make note of this, that we can manipulate this to turn it into the differential of the kth derivative. The next example introduces trigonometry to proof by induction. Whenever you are looking at a proof with trigonometric functions involved, you need to think about using trigonometric substitutions in order to complete proofs. You need to think about trigonometric identities to involve them in each step. We can see when n equals 1, the left-hand side is equal to cos of 2x. But the right-hand side needs some manipulation in order to show that it is equal to the left-hand side. Now let's think logically about what identities we're going to use. At the moment, our angle on the numerator is 4x. But in the left-hand side, the angle is 2x. So I can use the double angle identity here in order to change this angle into 2x. We can now see that things will cancel out, and therefore the left-hand side is equal to the right-hand side. Again, I will make my assumption for when n is equal to k. And now I'm going to substitute in for when n is equal to k plus 1. And again, you can see my goal here. So first of all, I substitute n is equal to k plus 1 into the left-hand side of my statement, and I have k plus 1 terms. Now I already have the left-hand side of the assumption in here. I don't need to do any manipulating, so I can just substitute in the right-hand side of the assumption. I can now write this into one fraction, as my goal is one fraction. Now I need to manipulate in order to reach my goal. When manipulating, as I mentioned, we need to think about using trigonometric identities. And let's think logically again. In my goal, the angle in the numerator is double the angle that I currently have. It's 2 times it, as the power is k plus 2, not k plus 1. I can see currently in my numerator I have sine of an angle times cos of that same angle. This looks very familiar, and it looks like the double angle identity for sine. However, I don't have the multiply by 2, therefore this is a half of sine of 2 times 2 to the power of k plus 1 x. The half can now be absorbed into the denominator, giving me a power of 2 to the power of k plus 1 on the denominator as required. This proves to be true for n equals k plus 1. So the key point of this, summarising, is that when you are performing proof by induction, or indeed any proof that involves trigonometric functions, then you need to think about identities. The statements we have already proven in the previous questions are not very common. But here are 3 statements, or theorems, that can be proved using proof by induction that are a little bit more famous. The first is de Moivre's theorem. The second is the formula for the sum of a geometric series. And the third is known as the power rule in differential calculus. The final proof requires the product rule to perform this proof by induction. It is also worth stating the limitations of proof by induction when applied to the first theorem, de Moivre's, and the third, the product rule. Proof by induction would only prove these to be true over the set of positive integers. However, both these statements are true for all real numbers, and would therefore require a different type of proof for the other cases of n. I'm going to now prove the first statement, de Moivre's theorem, as I want to show you that trigonometric identities are indeed important when completing proof by induction combined with trigonometry. I want to emphasize that point with this de Moivre's theorem. For this proof, when n equals 1, the proof is simpler, and there is no need to manipulate. Again, I will make my statement, and I will add the goal. I will now follow the structure for when n is equal to k plus 1. First of all, I will substitute k plus 1 into the statement. I then need to try and manipulate this to get in the left-hand side of the assumption. I can do this by breaking up the power of k plus 1 into the power of k multiplied by the bracket to the power of 1. This is similar to how I approached the first step of the divisibility proof in episode 2. I can now substitute in the right-hand side of the assumption. My next step will be to expand. The logical reason for this is because I want an expression with a real part and an imaginary part. I don't have that at the moment, but I can get it by expanding these 2 brackets. Again, as I mentioned, my goal is to have a real part and an imaginary part, so I need to separate these out. This makes the expression a lot easier to analyse. I now need to think about trigonometric identities, as I mentioned before. Can you spot the one to use? Try pausing the video and reaching for your formula booklet to see if you can find the correct identity. You should be able to see the compound angle formula of cosine in the real part, and the compound angle formula of sine in the imaginary part. The real part therefore simplifies to cosine of k plus 1 theta, and the imaginary coefficient simplifies to sine of k plus 1 theta. This is my goal, and therefore the proof is done. From this episode, it is important for you to again take note that my structure has not changed, regardless of the topic proof by induction has found itself in. More specifically to this episode, it is important that you take note of the manipulation I performed of the k plus 1th derivative, and it is important that when you practice the trigonometry proof by inductions, you have your formula booklet open on the trigonometric identities page.